Welcome to this second presentation on MATLAB and ROS integration. Today we will see how to integrate the kinematics and the odometry of our robot. Last time my colleague Alberto showed you how to set up the hardware and how to connect the ROS hardware to the Simulink environment. Today we will see the second steps, so the kinematics and the odometry. Let's start by the today agenda. We start by a simple brief introduction. Our robot have one input and two output. The input are the speed command that we want the robot to achieve, and the output are the lidar sensor outcome that we will see how to use in the next chapters, and the actual wheel command that are measured from the encoder inside the wheels. Today we want to understand how to manage these two main input and output, the speed command and the measured speed. The first module that we will develop is the kinematic one. So we want to transform the command bell, the speed command under the form of linear and angular speed, V and omega, into the correspondent omega ref left and omega ref right. So from linear and angular speed to the left and right angular speed of each wheel. We will use this module both in the input part, as you can see, but also in the output. In this way, simply changing the input and the output port, we can have from the measured omega left and omega right, the two measured speed of right and left wheels, we can have the Vm and omega m, the linear speed measured and the omega speed measured. The next module will be the odometry. The odometry is the module that from the actual speed measured of the robot extract the position information. So from the speed to the state of the robot. At the end, we will close this loop with the path following module. This module take the position of the robot and comparing to a path that will be our input to this block, produce a common speed that make the robot follow the path in input. But we will see step by step now how to perform these tasks. Summing up, we want the robot start from a starting point, the bottom right X, and go to the goal through a path that we will give to him. Let's analyze the first module, the kinematic one. Our robot, as I said, takes as input the speed command of the left and the right wheel under the form of angular commands, so omega ref left and omega ref right. On the other hand, we want to create a module that transforms the linear and angular speed command to this information. The first step is to take the command bell into the linear and angular form and use this transformation that is simple a kinematic transform. So as you can see, we can see that the V ref right, so the reference speed for the right wheel, will be the actual linear speed of the robot, with in addition half the angular speed produced by the command. So this simple transformation will produce from the linear and the angular speed the speed of each wheel. But in this case, as you can see, both right and left are linear speed. We want to transform this speed into the correspondent rotational speed in order to be given to the robot itself. This is simple. It is sufficient to divide each of the two speed of the right and the left wheel by its radius. Once we have done it, we have a complete module that transforms the speed command, the linear and angular speed command, into the angular speed of each wheel. That was our goal. But now let's see how to implement this in Simulink. So here we have a white and blank Simulink model. Let's start developing the kinematic model. So we need input. Let's start from the input. Two input in this case. So we have the V and the omega. Let's call the v in. So these are the two input, the speed, the linear speed command and the angular speed command. The first step is to, let's remember that the two equations were v plus and v minus. So we add a addition block like this. This one we put a minus because let's remember that in one case the omega, the rotational speed, enter in as plus sign, in the other case as minus sign. So we have our starting structure. Let's remember that the omega in, so the rotational speed that we want to apply, scaled by a factor of 2, but multiplied also by the distance of the wheel, the so-called wheelbase. So we introduce a constant that in our case is 0.3 centimeter, and now we can link the two with a multiplication block, with a product block. Okay, now we should divide the results of this product by 2. So let's select the multiply block and divide by 2. Let's connect this block to the add and the subtract block, and now we have completed the kinematic equation. So we take as input the linear speed and the angular one, and we obtain the two speed on the two wheels. So we can simply add the two output block that will be the left and right angular speed. So the v left, v right, and the v left of the two speed. Now actually our robot take as input the angular speed, not the linear speed of the two wheels, and so we can simply convert this output block into the angular correspondent speed. In order to do so, it's sufficient to divide the linear speed of the two wheels with these two divided block by the radius of our wheels. So in this case, we take the constant as before. Now the radius of the wheel is 0.045 meters, 4.5 centimeters. So we can simply write 0.045 and divide by this quantity. And now the output are ready to be sent to the robot. But now let's return to our presentation. So let's tackle the second module of this lesson, the odometry one. The odometry is a transformation from speed of the robot into the position, into its state. As we have seen, our robot gives us the information on the speed measured on the left and the right wheel. In particular, the encoder provides us to the angular speed of one and the other wheel. The first step is to transform these two information into the linear and angular speed. To do so is easy. We can use the previous developed module, the kinematic one, and this module simply transform the angular speed of the two wheels into the linear and the angular one. The second step, a little bit more complicated, is to write the equation of motion of the mobile robot. In this case, in a XY plane, you can see that a differential drive robot can be represented like this. We have a speed, a linear speed v, an omega that is the angular speed, and an orientation theta. We can see that with simply deriving this equation, x dot, the variation of x in the x direction, is a simple the v vector multiplied by the cosine of its direction theta. The same but opposite for the y axis. So y dot will be v multiplied by the sinus of the direction of the robot. Finally, the omega is simply the derivative of this angle. This block, of course, gives us the information on the derivative of x and y position. What we need actually are x and y, so we can simply add an integrative, this integral, that give as a feedback the theta orientation of the robot, provide us a vector of 3 elements that are x, y, and theta, the state of the robot, the position x and y in the plane, starting from the initial position, so when we switch on the robot, and theta, that is the orientation of the robot. Okay, now let's see the last part of this lesson, that is the path following. It will be the topic, the main topic of the next lesson, so we want only to introduce this topic, but we will go deeper in the next time. So our idea is to have a robot and its actual state, so let's suppose to have this robot in this position and provide him with a goal. We want the robot to follow this speed command in order to reach the goal. We will see more deep this module next time, so for now, let's suppose to have this module already given without going deeper. So now let's see the final demo, how to wrap up all of these parts, so the starting point where we developed the kinematic module, and next the odometry and the path following module into a single Simulink environment that can move our robot. So let's start. Okay, so returning to our Simulink workspace, we can see that we have our kinematic block completed. Now the first step is to write these two output, the speed right and left command, to the actual robot. In order to do so, we can simply open our ROS toolbox library and take this block, the publish one. The publish block take the input port, transform into a ROS message, and publish it to the ROS network in order to be read from the robot. The first topic will be the left speed. The second one, the right speed. Okay. Now, there are some peculiarities in writing a topic with Simulink, because we need to temporize the publication. In order to do so, we need to create a triggered subsystem. So what we can do is simply take, first of all, a blank message. So we can go there, we create a blank message. A blank message, in our case, we need a float 64. So we go to S, standard message. There is this. Of course, this should be decided according to the topic that we want to subscribe. So standard message, as you can see here, we can simply go to float 64. Okay. Okay, so we need to wrap this message with the information that we want to integrate. We can simply use the bus assignment. So we start from the bus that is created automatically from the block creating the message, the empty message, and we can simply link our omega right to the signal in input bus, and we can connect in output the bus. Same thing could be done for the other command. So in this case, the bus is created by the blank message. As I said before, we can connect now the information about the left speed into the integrating into the bus and connecting the bus to the left command. So what we are doing, we create a empty message of this type that we decide with the robot architecture. We put our information of speed into the bus, and we send through the bus to this topic, right command and left command. Now, as I said before, we need to trigger this subsystem in order to temporize the message. So we can simply click here and create a trigger subsystem. once we have done this passage, we can simply create a command to this trigger. So, for example, square wave generation and link there. Here you can select the frequency to generate the square wave, but it's not so important. So you can decide basing on how you want to your system to perform. Now let's put all of this system into a subsystem that we call actuator. Okay, so with this simple trick, we can simple command our robot with linear and angular speed. The second step is to obtain the pose of the robot through the odometry, as I said before. The robot pose can be read by two topics that our robot publish, and so let's take the subscribe, that is the opposite of the previous block that we use. Subscribe is a module that read a topic from a ROS network and create a corresponding Simulink data. So in our case, we will read the left speed, the measured left speed of course, and the right speed. In order to read this message, as you can see, there is a port that is called isNew that trigger each time there is a new message. So we should create a subsystem in order to read the message each time it is actually new. So first of all, we create a path selector. With only one output, because our message is composed only by one output. First thing, we create a triggered subsystem for both the case. And we trigger the subsystem only if there is a new message. Okay, so each time there is a new message, this block read the new message and put as in its output port. Now, in order to perform the kinematic transformer, we used a simplified method using a Simulink block. How we can do this? We have to transform this left and right speed into the linear left and right speed, so dividing by the radius of our wheels. So we create a product. We multiply by its radius, so 0.045. Multiplying, we obtain the linear speed of left and right wheel. Now we can use this block that is doing actually the same thing that I described to you in the presentation, but is more compact, that will perform the odometry. Let's go into the robotic system toolbox, mobile robot algorithm. We can take differential drive kinematic model here. We can select the vehicle input as wheel speed. We can connect. Now we have to select, of course, the wheel radius, that in our case is very simple, 0.45, and the track width, that is 0.3. This block is simply given in output through the integration, the state, so the x, y, and the theta position. So now let's wrap up this block that we call input. We have the state dot, and our input part. The end, that is the path following, so the third component that we left off is our path following algorithm. As I said, is not the topic of this lesson, but let's take this block that is the pure pursuit. Is a simple block that take as input the waypoints, so the goal that we want to place, the pose of the robot, and compute the linear and the angular speed. So The waypoints can be created simply adding a constant. So let's suppose, as in the case of the presentation, the first will be 1, 1, 0, and the second 1, minus 1. Okay, we can connect the goals to the waypoint. So these are our goals, and we connect the output of this block, so the linear bell and the angular bell, to our kinematic module. There are some information to be setted. So for example, the maximum linear velocity, angular one. The look ahead distance is how to approximate the different waypoints or to follow the path very strictly. Now let's put 0.3, that means to have a look ahead of 0.3 meter. So now if we run this code, connecting the robot as Alberto showed you last time, we can see our robot following the path.